Does anybody want me to shut off? Does anybody want to open a window over there? Got these ones open for me. Okay, good. Welcome back, everybody. We're just going to pick up on this lecture where we were last time. We're just kind of working through some problems right now. And the goal is to work out the posterior with maybe as few steps as possible. But just to kind of work through posterior, realize what we're doing, understand conjugate priors, and later in this lecture we'll try to think about which hyperparameters do we use in the conjugate prior. So I said that the conjugate prior for the normal problem, when we're just talking about mu, so I'm placing a prior distribution on mu, so that's this. I'm saying that the prior distribution, there's an equal sign in there, is normally distributed, and that results in a posterior that's normally distributed. And you can see that and verify it mentally rather quickly. Keep in mind, when we write down normal distributions, they look like that. So again, my random variable on the prior is mu, so it has special meaning. It's not any old normal distribution. I got to think about where I center it and how I use it. So that's those two things. So if I have this functional form right here, e to the minus quadratic form, I know it's a normal distribution. And so if you write other terms in here, you're just mucking around with the normalizing constant. It's really what you're doing in recentering it and rescaling it. So e to the minus quadratic is a normal, that's what it always is, it'll never be anything different than that. You know, if you see something that looks like e to the minus a positive linear term, you know that's exponential. So you know maybe it's a shifted exponential or something like that. So, but there's only two things to play around with in a linear equation. It's the scale, the shift, parameters, and the slope, and things like that. So normal distributions, e to the minus quadratic form. So if I multiply this into the likelihood, which also kind of looks normal, and so some people will call that self-conjugate. I don't care if you know that definition because most of my Bayesian friends, it's a textbook thing that you see pop up every once in a while. So the likelihood, the problem is normal, the likelihood looks normal, the prior looks normal, and the posterior looks normal. They all look normal. But all I really want you to know is that people call conjugate priors when the prior and the posterior belong to the same thing. And you can verify that if I add together two parabolas, two quadratic forms, that's another parabola. And hopefully in high school you drew enough parabolas that you could draw what that parabola looks like. So I could write out the likelihood problem. The likelihood function is either this thing, which is really easy to do. I could write out the 1 over 2 pi sigma over square root n and throw a square root sign there, and pull the standard error outside of there. That's the way I normally do it. But there's no real point in doing it because likelihoods are only defined under proportionalities. These have no great significance here. The significance comes from the sampling distributions. What I did is I thought about the sampling distribution for x bar. If the x size are that, the sampling distribution for x bar is this, and I don't lose any information about where the mean is by doing it this way. You can verify that because this equation, in terms of mu, is proportional to this equation. So again, things like that have no great significance. So you can just drop them because they don't include the mu's in there. Now I will point out and say this a couple more times. This function and this function are not the same functions in terms of the sigmas, or the sigma squareds are functions of the sigmas. But they are proportional, meaning that in mu they have the exact same shape. They're just scaled differently, raising them up or down, but the relative distances between points are always the same. So we're working through this calculation where we're going to find posterior distribution, and that's step 1 for us. So just in terms of a midterm, I'm going to ask you questions like this. Here's a prior, or maybe towards the end of class, I'll ask you which prior would you choose and why. And that's really what this class is about. And probably on midterm 1, I'll say, under this prior, work these things out. Which form of the likelihood should I use here? So I want to just work through this posterior calculation. When I ask you to write this down, I don't want you to just write down some mess of a function. I want you to say which distribution it is and identify that distribution for me. Tell me the underlying parameters of that distribution. And for a normal, that means tell me what the mean is and tell me what the variance is. So I don't know if it matters to you. It doesn't matter to me which one of these I use. Any preference? First one. So you can do the other one later. That's homework 1 stuff, due next Friday. So if you want to do it the other way, verify that you get the exact same answer. So again, I can get rid of this right here. I wrote down proportionality once, so I can start writing equality, but I always need proportional to the answer that I'm talking about. So I can multiply by any nonsensical constants. I can have them in forms that look like, oh, that's very interesting. You know, your mom will be impressed by writing that down, but nobody else will. So we'll just get rid of that. So we'll write down this form, e to the minus x bar minus mu. And I already like to spin this thing around. I get a little mental about this, where I'm like, I need to remind myself which one is the random variable in all this, and what I'm doing at every step. So my notation has to clue me into what I'm doing so I don't just get lost in the math. This problem's simple enough that you could probably work your way through it maybe in your head after doing it once or twice, but for a normal problem, like regular problems that are complicated, you want to start coming up with cues to yourself. So we don't get lost in all this stuff. So this is where we left off last time, is we just rewrote this. So I've got e to the minus 1/2 and e to the minus 1/2 here, so I'll just factorize those out and sum these two things together. I'm going to expand the square in one step while I do this. So mu squared minus 2 mu e plus e squared, and all of this is divided by v. V over here, v over here, and v. So that's all this stuff. Now we've got this stuff. So I've got mu squared here minus 2 mu minus x bar squared. And this is divided by sigma squared over n. This is an x bar in here, so I draw the term. So this is sigma squared over n, and this is sigma squared over n. So that's what I'm left with. So I look at this thing and I go, oh, that's a normal distribution. Now, if you write this on a midterm, I'll give you some points. But since you didn't take it all the way home and do like the real part of, if you were to take this to a computer and play around with it, I hope you could work out what the expectation of variance is first, so that you can invoke some functions that are already under the hood and start calling the normal protocols or know what you're playing around with. So, and I hope if you were talking to a scientist or something like that, imagine they came in with X, you know, cap X right here. Or maybe they were really nice and they came in with X bar for you and said everything's normally distributed. I would actually back them out real quickly and say I want to look at the real data. That you actually got it, and I'm going to verify whether or not that looks normally distributed and whether or not I believe X bar has that property quite yet. And so if the xi's are normally distributed, I believe X bar is normally distributed right away. If it looks a little bit of a departure or skewed or something like that, asymptotically it may become normally distributed, but I might not be willing to say it's normal quite yet. So it's a function of A. Now let's say they did that, and they said, Scotland, I need you to do a Bayesian analysis. I heard you are a Bayesian on campus. You can do some stuff for me. And I say, here's your answer. It's this. So what's E, what's V? I haven't told you. You can pick any E or V you want. I'm a subjectivist. So that's not going to help anybody. Got a question?
Yeah, so just with what we're doing right now, what is the normal?
Which normal is this? So the goal, which normal is this? So we know this is the normal.
Yeah.
And the question is which E and V. So I'm going to write them like this, E tilde, V tilde. They're getting updated. So we want to find these two things. That's the So let's just take this home, and it's really just algebra, and some of you can do it right away. If you know how to complete the square, do that, and identify the perfect square and factorize everything out. Instead, I want to just show you something that you probably already know. So this is how I would do it come midterm or final time, because I could just save some steps. So if I knew a couple things. So let's build up a mental algorithm so we can identify the expectation of the variance. So we know a normal looks like e to the minus 1/2 z, I'm going to call that the random variable, minus mu squared divided by sigma squared. So if somebody wrote this down for you, knowing what's out here could help you if you're trying to integrate over something like this. You would know what it would integrate to, but it's not going to tell you what the expectation and the variance are if you're working through a proportionality calculation. So already we've lost all the information, and this thing doesn't just have the variance tucked nicely in there. It's got a bunch of other stuff pre-multiplied in. So identifying it from this term by doing this will help. So if I had written everything out like this, and I could do that by completing the square, I'd know this is the mean, and that's the variance of the distribution. I could just rewrite this right here, e to the minus 1/2 z squared minus 2z mu plus mu squared over sigma squared. And this is over sigma squared, and this is over sigma squared. When I forget to write my variances underneath, just bark at me as soon as I finish writing. And I start talking. I do it all the time. We back up and put it in there. But that's what it looks like. This is the exact same equation right here. So one thing I can do is I can look at the quadratic term. So that's the quadratic. And what I notice is the variance is multiplying against it. So in problem 3 of the homework, you're going to be doing this in matrix form. So you're going to look for the quadratic term in matrix form, and you're going to take whatever that is, and the analog is you're going to invert it. It's going to be a matrix. It's sitting right in there. So you don't divide by matrices, you work with the inverse sign. So in this scalar problem, it's just divided, and that's okay. So you can hit written this is the variance inverse or divide by the variance. And so I just look at that thing and I look at whatever's multiplying against it. It's that thing right here, 1 over sigma squared. And so I know that the variance of z is equal to 1 over sigma squared inverted. So I'm just grabbing this thing and I'm inverting it over, and that's sigma squared. And we can do the same thing over here. There's quadratic term here, there's quadratic term here. I can add them together, and we'll do that in a moment. And I can invert that thing and know what the variance is of this distribution. So this is step 1. You do this first. Step 2 is find the expectation. So, and that can be identified here. It's a little hard to untangle here because this is all convoluted with normalizing constant stuff as well. It factorize out. So you look for the minus 2 linear term. So minus 2 linear. And it's got the expectation over the variance. You can see it right there. So you can't forget it if you remember what a normal distribution looks like. Just unwind it, and then you can build up these 2 steps. So that's the expectation times the variance. So what I do is I grab this term right here, whatever's sitting next to the minus 2 linear term, and I write it down. This isn't quite right yet. So I write down mu over sigma squared. And that's not the mean, that's the mean over the variance. But I just found the variance in step 1. So what I'm going to do is I'm going to grab this thing and I'm going to multiply by that, whatever I found in step 1. And that always unpacks the mean for you. So that seems worthless if you know this form right here. It's totally worthless. If somebody had this form, I would never unwind it and then identify the terms. But if something weren't packed up real nicely and it was already unpacked, then I would use that algorithm to identify the terms. And let's just do that. So I'm going to rewrite this thing. Right here is e to the minus 1/2. And I'm going to write out the quadratic term first. So I've got two pieces for the quadratic term. Right here I've got one, and right here I've got one. So I'm going to add those together. That's 1 over v, and this is 1 over sigma squared over n. So that's multiplying there. I'm ready to tell you what the variance is, but I'm going to keep writing and just get this thing right. Minus 2 linear, and I've got two minus 2 linear components as well. So I've got this one right here. So that's e over v plus this one. So in that term is x bar over sigma squared over n. And I could, if I felt like wasting some chalk, and today I do, so I could write this other stuff out. So I could end up writing out this is a plus right here, x bar squared over sigma squared over n plus e squared over v. And I could do that and write all that out, but this is junk to me. And the reason why it's junk is I could have just done this and closed this brace up, this one going with this, and rewrote another e to the minus 1/2 right here. And just grab this term and factorize it out. So that's just how exponents multiply as you add together their exponents. And if I look at this term right here, I know that. That's a constant. That's a constant in my problem. I get to know sigma squared. Not if I didn't know sigma squared. If I didn't know sigma squared, this isn't a constant, but for this problem it is. I know e, that's one of my hyperparameters, and I know v. And so this is all constant. So usually I get rid of that, and I just do this. And I stop writing. So I only look at the quadratic term and the minus 2 linear. Once I have everything in this form, I'm ready to tell you the whole answer. So this right here is a normal with expectation e tilde and v tilde. Let's just write down what those are. Give myself some room. V tilde first. So step 1, I look at the quadratic term and I see that stuff right here. So it's 1 over v plus 1 over sigma squared over n inverse. That's it. Bam. You can rewrite this if you want, and you can do what your 4th grade teacher insisted you do, but if you write it like this, I like it. So, and Chris is going to go upstairs, 4th grade teacher. So start writing too much. And you can do that. So I like to waste time too, but I don't like to waste time like this. But I do like to think about the invert of variances. So I want you to just think about what this is. The invert scale of the variance has just as much meaning as the variance scale. So I would agree that expectations to us feel more natural. But just keep in mind to trick yourself. So, but it's like the center of the distribution. Usually whatever units we're talking about in, we're in the same unit scale. I think you can do that with taking the square root of the variance. But variance is some like mathematical form of measure of spread, and it doesn't apply to every concept out there. And variance, the squared deviation between things, is a perfectly mathematical thing. And I never met a human that thought naturally in terms of variance. Usually I would think you would think in like absolute distances or something like that. You know, saying that, if you think in quadratic variance and you liked your high school class and you think of everything as the Cartesian plane, cool, I live in this world. So that's not what I think about. So, expectations feel more natural, but variances are just some concept of spread. So if I think about variance, I can think about the inverse of variance too. It's no more complicated of a concept than squaring something and taking the deviation. So I'll just write this down. So definition, precision is the inverse of variance. So very often, we'll write down phi for that parameter. All my friends use phi. So just like all my friends use sigma squared and mu's in normal distributions. So this is pretty clear. So if the variance of something is large, your precision is very small. You're very imprecise. And if you're very precise in measuring something, so this is big, then the variance is small. The distribution is tight. So just a concept like any other concept. So for this problem, the precision's out. And then I put it back on the variance scale. So if I were working at precision, so we just added those together and identify the precision. But since we like to talk about variances, I'll flip it back over for you. So, and I think that kind of makes some sense. The expectation is a little bit more interesting. And we can think more about that. Like I always at least do a sanity check on my expectations. And go, is that what I expect? If I don't expect that, and I'm like, yeah, I mean, no data is over there, but this is my expectation. Even if it's true, I don't think that's a super useful concept to somebody. But in this case, in normal distributions, everything is tightly surrounding the expectations. So I think it kind of makes some sense. So what do I do to get this thing? I'll call it double R. So, because I can't write my E's somehow a lot of times without putting double. So, and I'll put double there. Get equal emphasis. So I follow step 2. Now keep in mind, if this was problem 3 on the homework, you're going to be multiplying together matrices and vectors. So make sure they're conformable and you do it in the right order. Only one order, like, it's never tricky. It's never like, is it this or is it that? If you know what the problem's asking, you know what the dimensionality of the problem is, and in this problem, for problem 3, there's only one correct way to do it. The other thing doesn't make any sense. So if you try to multiply it together, nobody would understand what you're talking about because it's not a legal mathematical language. So in this problem, because everything is scalar, it's no big deal. So what I do is I grab the -2 linear term. It's here. Whoops, it's here. So E over V plus X bar over sigma squared over N. And I multiply by this. 1 over V plus 1 over sigma squared over N. Inverse. Now let me just write this a little bit differently. Divide. Okay, it would have to be an inverse if that were a matrix, and that's what it is in problem 3 of homework 1. But I'll just write it like this. And the reason I like to look at the answer like this, I understand that if you go to Wikipedia, or you go to Cassell and Berger and they do this problem, they will unfold it all. I like it just like this. I'm totally satisfied with the answer looking like this. If you want to unfold it and think about it a little bit differently, that's valid as well. And I can recognize both answers. So this is just E right here, not the whole thing. So this is my prior expectation. I'll say this is where my likelihood is centered. And they kind of have very similar meanings. So this was for my prior distribution, the center, and this is where my likelihood is centered. So similar concepts. And I'm taking an average of these two things. So I'm averaging with this weight, 1 over V, and 1 over sigma squared over N. Those are the weights on my average, and this is what a weighted average looks like. So now I divide by the sum of my weights. So a weighted average is you multiply by your positive weights, sum everything up, and then you divide by those weights. So let me just write that down. Weighted average. It's just sum of the WI's times, I'll say, the XI's divided by sum of the weights. So I'll rewrite this just real quickly as sum of the W tilde I's times XI, where the W tilde I is equal to the WI divided by sum of the. I probably need to say one more thing. The WI's themselves are positive. As I can include zero and nothing bad happens there. I can take something out of the equation. So that's just what weighted averages are. So if you want to think of that as a probability, this is a number between 0 and 1, and that's what ends up happening. So I still like to write it just like this. This is sum of the weights. These things are positive. If I like to think of the weight as 1 over v divided by this, then that's okay. Or I can divide it all on the other side. So this is just a weighted average between what my likelihood is telling me and what my prior is telling me. So it's that superposition. So normal distribution, the likelihood is here. Centered at XR. Prior is here. This prior is here, expectation is there, and the posterior distribution is in the middle. And it's centered at E tilde. That's what's going on. So how much weight am I putting on these two masses? It depends on how tight my distribution is. So this is getting tighter and tighter as n gets bigger. So the likelihood is concentrating. And this likelihood is climbing up, just like we saw in the beta distribution. That thing was getting taller and taller and shooting off the screen in all my simulations. So I let it run long enough. I kind of like that. That's getting more and more certain about where you think the parameter is. So that gets tighter and tighter, and that stays the same. And one question is how do we pick this parameter right here? So obviously, it's the thing that is concentrating mass around E. And the question would be, is this a good picture right here? If somebody came in there and said, my likelihood's there, my prior's here, my posterior's there, I would say, why are your likelihood and your prior such a mismatch? And your prior so concentrated around this answer? Now that might be the right thing to do, that you just have two studies and they tell you kind of carve the answer in independent fashion, so you can multiply them together. And you get the answer, and it's in the middle. I've never seen an analysis like that I really trusted. I'm like, why isn't everything telling you the same stuff? Why is it all these different directions? We're missing something. And that I can accept. We're missing a part of it, and we think that the answer's in here, and maybe this is the way we justify it to ourselves. But it'd be hard for me to swallow that that is tighter than that. And so I might be thinking, I really want my prior distribution. If I'm going to center it over here, this is what I thought before. I want this to be way more diffused. And so I like to look at people's priors and see, do they overlap what the data is telling you? And sometimes the answer is absolutely no, and there's something super interesting about that. We can talk about those examples later on when we get into subjective conversations. I really just want to get you to calculate something right now. So we're thinking that this variance should be big. So how big is the question? Chris, if I just gave you a problem like this and I said, I want to learn what the mean is in a normal distribution, I'm really grappling with this prior variance right here. I know what E is. I feel really good about it. But not so good that I'm willing to make V small. I want it centered over at this number. Can you advise me?
Well, before we did it with uniform,
Oh, so you'd say infinite. How do I code that up?
just use uniform bias.
Oh, a uniform prior. So I don't want to, because I don't know a uniform between negative infinity and infinity. I'm unwilling to subscribe to this concept yet. Maybe.
So, if you were to use variance, would it not matter where
And we're getting there. You know, half of you can see exactly that. If I blow this thing up and I make this so big, it's going to drive the size of this thing down. And all of a sudden, E won't even matter. So what would be a good number if you were just to give me a number and you didn't know anything about the problem, you didn't know anything about how good I was at picking E's? Give me a number. One. Holy smokes, tiny number. So, okay, so we've got bias on our hands, that's loud. So, bigger than sigma squared over n. So, since you know what sigma squared over n is, because you know n and sigma squared, you can use it as a reference point. So I think that's a really good answer. Bigger than that, at least. Wider than that. How much wider? Maybe 5 sigma. Yeah, exactly. So maybe if I did something like this, let's, oh my gosh. You see it?
The sigma squared is dependent on the data. Correct.
Yeah, so we wouldn't know in general, but my fiction of this class is you get to know it.
So are we allowed to use that data to inform our prior?
You didn't use data to get sigma squared, I gave you sigma squared.
Oh, okay.
So that is the fiction that I'm giving you. So I get it. Yeah, exactly. So good. Ask me that when I actually do some abuse. So right now my abuse is just imagining I have sigma squared. So this is perfectly classroom type of exercise. You'll learn sigma squared in a moment.
If you did B bigger than 6 squared over n, can you be sure that like your posterior variance will always like reduce the correct one?
Yeah.
Like always. But if they you might be underestimating the variance?
I don't think so. I think it always blows up variance. It always adds variance. So uncertainty in the prior just adds variance to the process. So it's always going to increase the variance guarantee. Let me just write down this answer that you guys said. So maybe I should pick V to be 5 times sigma squared. I heard this and I kind of liked it. So let's just do this. So maybe this, or let's start a little bit simpler. Let's just say sigma squared right here. If I said V was sigma squared, how much weight am I cutting on my prior? We did this kind of when we thought about the beta prior. We talked about beta half. Half was acting like a single data point. So if I pick V to be sigma squared, how much weight in terms of data, if we think about the prior as a fictitious data point, I don't think of it as that way, I just think of it as weight. But if you wanted to think of it as a fictitious data point for the moment, how much weight would this impose on E in terms of a data quantity? Huh? It's n data points, that would be n data points. No, 1 over n data points. Okay. So it'd be 1/30 of the data point, 1 over 31. Where are you getting n from? It'd be 1 over n the whole sample. So comparatively. But it wouldn't be 1 over n of the data point. It'd be 1 over n of the sample. So the sample's n data points, so 1 over n of the entire sample is like 1 data point. So this is like worth 1 data point. Something like that. So if I did something like this, divided by k, this would be worth like k data points. K is equal to 1, it is 1 data point. So you can think of it like that, and you don't have to get super technical, super early, and start taking limits. You can kind of just look at everything here. So I kind of like that. And then I like David's answer. Don't divide by it and start making it worth more, make it worth less. So how many data points is that worth? Now your answer might be right. That's worth 5 data points, a fifth of the data point. So that's like a fifth of the data point. So less on there on E. So I kind of like that. So if I had a sample that was relatively small, like 9 data points, I definitely would be thinking about that in terms of my prior weight. If I had a bazillion data points, okay. And so I'll just kind of point this out. This was an interesting question over here. So this is just an aside question while we're thinking about this problem. I'd like us to build up some intuition. If my likelihood, so aside, if my likelihood looked like this and it was normally distributed, that's the 0 one right there. It's asymptoting into. So my likelihood look like this. Centered at X bar. Okay, it has some spread. I'm not going to tell you what that number is. In my prior distribution, also looked like that. Right on top. Just generated for illustration. So my prior looked exactly the same. Now this would get into your question. What? You centered your prior at X bar? You better justify yourself because you double dipped your data. And this is why this is a concern. And I would say you have to be really careful if you did do something like this, and there's a class of Bayesians called empirical Bayesians that will do this. If you just shortcut it and center it in your data, everybody will bark. But if you do it through a process and tell them what you're doing and why, they'll go, oh, that might be why you do it. I was an adamant non-empirical Bayesian. I thought it violated way too many philosophies for me. And I thought, some problems you kind of have to do.
Is it okay to look at your data and then go to the prior and then use your data to somehow like justify that? Like say, here's my data, this is kind of what it looks like. I'm going to pick I'm going to pick a prior that looks like my data, and then here's 3 other reasons that are unconnected to my data. Is that to justify as far as that how you do, or should you create?
To cowardly answer your question. Maybe. But let's talk about it. So I don't know. I don't want to give you prescriptions quite yet. But I would entertain the idea. So violation of the likelihood principle, and it's going to upset some of my professors. But that's okay. So if I think that it's actually going to lead to a good answer, you've got a good explanation. Sell it. So I don't know. So I used to say that it was really silly to do these things. Now, if my prior was exactly matching the variance, I'd say, yeah, right. So I don't believe you at all, give me a break. But if you did this, let's say your likelihood looked like that, and your prior looked like that, what would your posterior look like? Same thing, right? So Chris says same thing. Anybody?
Wouldn't your variance be like that?
Yeah, your variance would be getting smaller. If it were the same, that would be the uniform prior. So my likelihood and my posterior are the same if I use the uniform prior. And I multiply by 1. We've seen that. So that can't be true. So if I multiply by 2 functions and I got the same answer. So this is actually, the posterior will get higher. I don't know if I have that exactly right, but the posterior will concentrate when you do this. And I encourage you to work out what exactly that variance is, and you can do that through this calculation. So you could figure out what the variance was if my variances were the same and I had them together. The answer is sitting right here. So what I would have done is taken v to be sigma squared over n, and that's certainly not. So you got, boom, 2, 1/2, and flip. So awesome. Yeah, so it collapses. And what you're really saying as a Bayesian, if you were to subscribe to the subjective sort of way we phrase Bayes, i.e. this is what I believe a priori, I do not say that it incites people. So, but if I believe this a priori, and then I went out and collected data, I'd be like, yeah, I'm really sure about that. I don't even know if this would like portray how certain I am about X bar. If all of a sudden it happened just like I presupposed, that would be amazing confirmation. So
I guess like rephrasing my question from earlier, if you pick your prior to have a variance that's bigger and you plug your data, your posterior will converge to the right variance. But if you pick a prior that has a smaller variance, you won't converge.
Oh, if you're saying if I make this infinity and drive this thing down towards 0.
Yeah.
Yeah, you're right. You're right. Eventually, if I drove this down to 0, that's the point mass prior. So that would be a very complicated way to phrase the point mass. But you're absolutely right. And I would cut the infinite mass on this. So I take that back. So you're right. I'd stick everything to the prior. That'd be a bad idea. So I wouldn't want this variance right here to be tiny, i.e. saying that my prior is super precise and very sticky and you can't get away from it. Okay, let's take this to an extreme. So I agree this should be some number that's bigger, you know? If you have a lot of data, it won't matter unless you drove v to 0, which is supposed to be off limits. So that one, I'm at least courageous enough to say definitely don't do that. So that's what I call a political prior, and you'll never change your mind with any data or anywhere. So dogmatic priors is what Jack Wood calls it. That's probably better. Let's look at this. So let's just think about this equation in the limit. What if I just made v super big? And what I mean by this, if you don't like thinking about infinities and they bother you, take this number to be something like 10 bazillion trillion. Big numbers, I don't know. What's the biggest number you know? Half a God knows a number or something like that. So, big numbers. Yeah, I'm stuck at trill too. I can't think outside of it. I don't know what that means. But some big number that I don't know what it means, the GDP raised to the GDP raised to the GDP raised to the GDP raised to the GDP. I'm getting real big here. So, and I end up just looking at this thing, expectation over variance plus x bar over sigma squared over n, 1 over variance plus 1 over sigma squared over n. If you'd like to do L'Hopital's rule, please do that and get this thing right for me. But I'm going to do some grad school limit taking real quick. So, v is big, so that's going to 0, and that's happening here too. I get it. Do L'Hopital's, get that right. You will do both of those things. So, that's 0. That's 0. I'm going to take this thing off. It doesn't work out. And the reason that works out and you can do this is they're anchored into something positive that's not moving. So that whole denominator isn't flying off towards 0. So if this was going off towards 0 and that was going off towards 0 and I did that limit like that, then my old grad student TAs, I would give them the point about, you're right. You know, that wouldn't work. But in this case, it definitely works and it's definitely adjustable. So if you like to do it more formally for your grad GTAs, now you're more than grad GTAs, so you decide. So that's what I'm going to do right here. So this answer is x bar over sigma squared over n times 1 over sigma squared over n inverse. And those things cancel each other. And this is x bar, is where it's set. And so you get back to an answer that we already liked. So I've only given you a way to think about things. And maybe that's nice to you. Maybe you think, maybe I didn't need a base class because I already liked x bar. And I would have already said sigma squared over n probably is the variance attributed to that estimator, and I have a different way of thinking about that. In an inference class, that's what we kind of start with. The old way of thinking about it. This is kind of new, but it's pretty old too. So Laplace did this a long time ago. This is hundreds of years old. And Laplace even talked about the prior that you get. So the normal distribution, E, V, right here, looks like this. Centered at E. It's got variance, something like this. I like to put the square root over here. So if I make this thing bigger and bigger and bigger, I'm flattening out this distribution. There it is. Flatter, flatter. And if you're good with how flat that is, use that prior, just as long as that variance is much bigger than your value is. And I'll be okay with that. I'm courageous enough to say, we'll at least numerically agree with each other. So maybe y'all at 17th decimal point, that means nothing to you, you don't agree. You don't even have enough data to measure that. That's cool. So I'll take this all the way to a limit and imagine this thing is perfectly flat. And that's what this means conceptually. I personally, sometimes when I explain this, I don't like thinking about this, and I don't like to think about properties of the prior because the prior doesn't have any properties. I like to think about properties of my posterior. And this would be x bar, and this would be sigma squared over n. I think that's a totally reasonable answer for all kinds of reasons. So you might have reasons that are similar to mine. So I'm not thinking about properties of my prior and what the prior distribution means. This right here, when I load variance off to infinity, and I call this perfectly flat, that's not a distribution. So this is what's called improper. So let me tell you what an improper distribution is. First tell you what a proper distribution is. A proper, I'll talk about a density f of x, f of z has the property over z, whole universe, definite integral, fz dz is equal to 1. So it just integrates. Now, people like to sometimes not normalize their stuff, and this can just be some finite value. So sometimes they don't normalize the integral, but if you were able to compute this and you had something to find out the proportionality, you could compute that and normalize it with that number. And instead of writing that, people like to write this, not infinite. Less than infinity is the very typical way to write that. Well, all they're saying is that integrates to an actual number. If you integrate over this, it's got infinite mass all the way forever. You're going to keep adding stuff forever and ever and ever. The tails aren't coming down. And you start adding so slowly that it becomes so negligible it converges to something. Just because it's coming down doesn't mean it's going to converge. It doesn't come down fast enough. That doesn't come down at all. It's a flat line. And so that's what's called an improper distribution. So let me just write that down. An improper dist is not proper. The worst definition in the world, I'll tell you what it's not, and then I'll give you it. I'll do that once more in this class, and usually I'll give you real definitions. So we can do two real ones. I don't think about that too much, but I do want to think about it just a little bit more and talk about invariance to linear shifts. And so if you've heard me in my inference class talk about that, I want to be more specific this next time. I also want to talk about this problem on Monday. Sigma squared over, or given, x and mu. So I'm just going to talk about the mean is fixed. It's as good of a fiction as the one we did the first time. I will give you a heads up. We will use these distributions in class. They're actually a practical utility. So I'll show you where later when we do give sampling. But remember, this thing is just likelihood, sigma squared, x in mu. And I need a prior distribution on sigma squared. And I can write down what this looks like. This is root 2 pi. I'm going to write the sigma squared in here. This gets powered up to the nth power, e to the minus 1/2 sum xi's minus mu squared over sigma squared. So now I'm using that other form of likelihood. And I could have written it down in simpler form, but I might not know how to do that. And use S squared as the sufficient statistic. It turns out it is, and I can re-encode this using S squared, but that's not as familiar to us. So you'll do that on homework too, is rewrite everything in terms of S squared. But this is the same formula, it looks like, on the chalkboard, but now I'm thinking of this as a function over the sigma squares. And I'm going to ask this question: what is the conjugate prior for sigma squared? And you have to stare at the form of this to know. I cannot get rid of this right here. I could get rid of that stuff. But I can't get rid of this anymore because that's what I'm trying to learn about. So what is the conjugate prior for sigma squared? Mike says gamma. Anybody agree? So somebody says gamma. So sigma squared showing up like this, right in there. I've got this out in front. Is that what gammas look like? Gammas look like this. We'll come back to that next time. So gammas look a little different where this is the random variable. It's inverse gamma. So it's the upside down of the gamma. It's like this. So this isn't quite right. That's wrong. But 1 over z, 1 over z. It looks more like that. You're not taking a gamma distribution and flipping that random variable upside down. I don't want to teach you about an inverse gamma. I want to teach you about a gamma distribution because that's what more people are familiar with. You could answer this question, but instead, what I'm going to do is I'm going to say, forget that thing. I'm going to talk about this. Phi is 1 over sigma squared, and I'm going to put the prior on that. That ends up just taking that there, and this will be 1 over phi inside there. That will get kicked upstairs. This is in the right place. That's what a gamma looks like. This is the precision parameterization. So if I put everything on the precision scale and think about it that way, I can use the gamma answer, and I don't have to use a new distribution. I will say this: if you know everything about a gamma, in theory, you know everything about an inverse gamma. And with a computer in front of you and a quick Monte Carlo simulation, you can compute whatever you want. But that doesn't mean in practice you know everything about an inverse gamma, and that would store a little bit of RAM in your brain. So I'm going to obviate that, and we're not going to talk about the inverse gamma more than just knowing that is the conjugate prior for sigma squared. But we're going to move this around and talk about gamma. So look up what a gamma distribution is for Monday's lecture, because we're going to be kicking it off now. We're going to first talk about shift invariance, and then after we do the conjugate analysis for precision, we're going to talk about scale invariance and what that actually means. That's it for now, guys. Enjoy the weekend. If you need anything, I've got a couple minutes after class, and I'll just hang out. Sorry for going over. I will give you the time back at some point during this